Exactly.
It's orders of magnitude worse in gravity. The constraints are much stronger.
But I would hope in something like the matrix quantum mechanics, you'd have a shot at importing a lot of those ideas where basically the constraints are similar. You know, it's another Gauss law. Sort of.
Yeah, but how do you think about entanglement locally in space?
Yeah, it's a question. The first quantized picture is tricky.
Very confusing.
But I don't think impossible.
Well, no, I think yeah. But how does that relate to this inner space? I know not to this inner space, but what can you do with it?
Well, I was thinking about like a piece of matter crossing a horizon, like you said. I'm thinking working at a sort of linearized level, and you can relate the change in entropy to basically the Rindler Hamiltonian, sort of the Hamiltonian on these light sheet surfaces. And I thought it might be useful to start thinking what the Rindler Hamiltonian might look like for some of these matrix theories.
Yeah.
Try to relate that to entropy. Yeah.
Right. Oh, okay. So, okay, so I preempted the class. Preempted, is that the right word? What is it called when a pirate comes and takes over a ship?
Yeah.
Commandeer.
Commandeer.
Yeah.
Commandeer.
Could be worse. It could be worse. The class, because I wanted to finish up last time. The issue of precursors, switchback effects, and how we connect those things to black hole physics. And then discuss a little bit the second law, both the second law of complexity and the second law of thermodynamics. And one particular simple aspect of it. Okay, I don't remember, I can't remember how far, this is every week, I never remember exactly where I left off this week. So that's why we go so slow, because, you know, it's 2 steps forward, 1 step back, 2 steps forward, 1 step back.
More thorough that way.
I don't know if it's any more thorough, it's just slower. Good. So we started to talk a little bit about circuits, and precursors, and epidemics, and logistic functions. I still haven't found out why the logistic functions are called logistic functions. It's got something to do with the logistic map, but I don't know what the logistic map is.
So Aitor and I looked this up after class because
Yeah,
of
right,
logarithms
right.
as well. Apparently it came from people computing logarithms, and that in the
LOG?
army. Yeah.
LOG?
Yeah, and then it was a sort of very...
What's it got to do with, I know, but logistics?
So logistics were the people who compute logarithms in the army, because apparently...
People in the army who compute logarithms?
It was apparently a hard task to do.
Yeah, that's a hard
And so that's where they
This
came
was,
from.
they needed this for artillery or what?
I think so. I'm not really sure where logarithm comes from, though.
Well, you multiply numbers.
Nice parabola.
The average soldier doesn't know how to multiply. That's, no, I don't know, but that's true. You don't know that's true. It's probably pretty very good.
No, this is not true.
I see. So that's where the word logistics came from?
This is the prevalent views of the term logistics comes from the late 19th century from the French word. That's why it's particularly
French word what?
logistique, meaning to lodge.
To lodge?
A lodge, but that has nothing to do with logarithms.
I'm not gonna. We'll send out an email with the proper citations.
No, I mean, logistics in the army,
Yeah,
and
so
things
I
like
thought
getting
logic
into houses.
There was a
to
French
live.
guy who was studying population growth who
Yeah.
first gave the same logistic, like François Villejuif, whatever.
Because he wanted to know, make sure he had enough houses for the microorganisms to
Yeah,
live in.
okay, so that is actually.
Yeah, there's some connection there, I assume, but,
This is
anyway, the logistic function. Okay, let me just go back and review that a little bit, what we said. Okay, so what we're really interested in is Hamiltonians and field theories, not random quantum circuits and qubits. But we don't have the power at the present time to really talk about the things I'm talking about in the context of a real field theory, and so we play model-dependent games. The system that we were talking about last time consisted of a set of qubits, of which I always have to draw an even number, otherwise I get into trouble with my rules. And circuits, quantum circuits, which just mean quantum evolution, with a particular kind of circuit design, which is intended to reflect as closely as possible the evolution of the Hamiltonian. Well, hold on, let me go back a step. Let me go back a step to black holes and ABS and CFT and all of that stuff. Let me give you a picture of how I picture the relationship between black holes, qubits, fast scrambling, and a quantum field theory, in particular, a large N quantum field theory. I think of it the following way, that at each vertex of a quantum field theory, you have a set of degrees of freedom, which could be matrix degrees of freedom, typically matrix degrees of freedom, but they're such that they're all coupled to each other in all-to-all kind of coupling. K-local, meaning to say that they only occur in small groups in the Hamiltonian. And so let me represent that by saying each lattice side of the field theory, I'm making a graph to represent the Hamiltonian. Everybody couples to everybody else. Is everybody coupled to everybody else there?
Okay.
Everybody couples to everybody else. And that's a picture of what goes on one site. And then there are many sites. So forth and so on. All right. These sites are not independent of each other, they couple to each other. So let's put in a few more links. Links connecting these things together like this. The number of degrees of freedom at each site, for example, for a two-dimensional field theory, is just a central charge. For a gauge theory, it's typically proportional to n squared, and so forth. I'll just call it the central charge, whether it's two-dimensional or not. Number of degrees of freedom. And then there are two kinds of, well, let's see, scrambling. Two kinds of scrambling that takes place. If you perturb a small number of degrees of freedom, let's say on one site, then information spreads out in two ways. One way is within a site, and that's this kind of fast scrambling that is typical of systems with all-to-all couplings, K-local all-to-all couplings. And then in addition, I was going to use the word diffuse. I don't literally mean diffuse. It's not diffusive. It's a kind of propagation, I guess you can call it ballistic propagation, which takes place between sites. Okay. Full scrambling of a full field theory involves both. One happens fast, it's the fast scrambling property. And for that, the typical scrambling time, which I'll label according to the notation T star, that's typically logarithm in the number of degrees of freedom, which is called log of, I guess it's log of C, log of the number of degrees of freedom. That's how long it takes for the system to spread its perturbation out among degrees of freedom at a site. And then, of course, after that, it propagates, well, not only after, sort of simultaneously, it propagates through the system in the way that a field theory would propagate. But I'm much more interested in what happens here. Okay, what happens in one of these. Now, we can go on and say something else. What goes on here is comparable to what goes on in a black hole. Well, let's imagine first of all, here's ABS, and let's suppose we have a large black hole, a high temperature black hole. A high temperature black hole looks like this. The field theory, the horizon, occupies a lot of sites along the field theory here, and each site has n squared degrees of freedom, or c degrees of freedom. So the whole black hole has an entropy which is proportional to the number of sites times the number of degrees of freedom at each site. Okay. Smaller black holes have fewer degrees of freedom, not because c is smaller, but because the effective number of sites that's important is smaller. We don't need to divide the field theory up into so many sites to be studying a more infrared problem. And eventually you get down to what you can think of as the smallest stable black hole, the Page-Hawking transition black hole, which occurs when the black hole Schwarzschild radius is basically the anti-de Sitter radius. That you can think of as a unit like this, whose entropy is just a central charge. And so each one of a large black hole is simply, in a certain sense, a system of coupled unit black holes, let's call it that. Now this can be made more precise. I don't need to make it more precise right now. I'm just telling you now why I tend to focus on the sort of minimal sized black hole, the one whose radius is proportional to the central charge. There's no reason that we can't study by similar methods the bigger black holes, but it's sort of just repetition of the same thing together with some ballistic propagation between them. It's almost as though a large black hole was just a collection of smaller black holes with some coupling between them which allowed signals to transfer between them. All right, so I just mentioned that. Now, the quantum circuits that I'm interested in are really these things. A set of quantum circuits where, a circuit where everybody can interact with everybody else. Yeah, Jordan.
I mean, there's a sense in which this is very striking resemblance to this, these coupled SYK models.
Yeah, except the coupled SYK models, correct me if I'm wrong, but I think they imagine each one is separately random relative to the other. That's not the kind of thing we're talking about, I think. That would not have translation invariance, for example. You have a different Hamiltonian here, and here, and here, and here.
Ah, okay.
And that's the only reason you can solve it,
Yes.
because you're doing enough. Okay. Generally speaking, the more you average over, the easier it is.
Yes.
Right, the more you average over. It is too hard to take a random Hamiltonian on one side and then replicate it identically on all the sides. That's just too hard. So you do a different thing, but it's at the cost of a lot of physics.
Sure.
For example, there's no translation invariance anymore, because when you go from there's a translation invariance of the ensemble, but that's different than translation invariance of the system. Each member, each instance of the ensemble does not exhibit the momentum conservation. Okay, so in that sense, I think it's not really similar, or at least not completely similar. All right, so we're imagining now one of these sites which has a large number of degrees of freedom, which we're thinking about as qubits. I don't even really know that how much of what I say is really necessarily you have to think about qubits, but it's tempting to want to. Yeah.
This unit black hole that you're saying is morally like one site.
I never said morally.
Oh, you just said it's like one site. You said it's like one site.
I said like
As
one.
being more, okay. So it's not like a single site on the boundary, it's like
It
an
is.
S wave of all this, it's
No,
like
no,
a
no.
single site, but like.
It is a single field theory site
Yeah,
within squared degrees of freedom.
but is it like looking at only it's not like a particular single site on the boundary?
It is.
Oh, it is?
Yeah. A single
Which
site,
one?
well, all right, depends on what you mean by a site, but let's decide what we mean by a site. By a site, we mean a thing which is rich enough to have n squared degrees of freedom on it. Why n squared? Because that's the number of fields.
If it's like a rotationally symmetric setup, then it's not a particular site on the boundary, right?
It's not a
Because
particular
it's
site.
equally,
Everyone-
it's
everyone's
like the
like-
S wave of all the sites or something, or.
No, I wouldn't say that. I would say when you go to the boundary, or very near the boundary, you regulate the theory. You regulate the theory, for example, one regulation of the theory would be to make a lattice theory out of it.
Mhm.
The way you do it, how many sites do you regulate it into? Well, the rule of thumb is take this point over here and just move outward in a particularly prescribed way, and take each one of these little cells and think of it as a site. You can literally do it by the geometry of a triangle there. That tells you how many cells there are. The number of degrees of freedom is the number of cells times c degrees of freedom for each cell. So I would say that each cell here is like a matrix description. Now, if we focus, that's what I would say. I would say each one of them is.
If there's a single small black hole in the center, though, which cell on the boundary does that correspond?
Oh, no, I see what you're asking. No, that's right.
So it corresponds to like all of the, like some rotationally
yeah.
symmetric.
Yeah, so perhaps another way to say it is, we can think of this in terms of renormalization.
Yeah.
We don't need this many degrees of freedom to study the infrared properties of the field theory. So we tend to integrate them out. In integrating them out, we move the cutoff in, and we break the system up into fewer lattice sites. Each lattice site, in a way which we really don't know how to do, but each lattice site here then is some cumulative average in the renormalization sense. There's a bunch here. We keep doing that until we get down near the center someplace. There's only one lattice site left in the limit where we want to study just one ADS radius whose maximum entropy is C. Nominally, we only need one lattice site.
And you thought about what that one lattice site is in terms of the degrees of freedom before we did all the coarse graining?
Yeah, it's
And
some,
it looks
it's
like-
just what you said, it's some, I'm reluctant to say it's an S wave, but it's
Yeah, I just
some,
thought
it's
that.
some.
Low energy degrees
Yeah,
of freedom.
yeah. Yeah, it's, right, okay, so our rule is, in the random circuit model, everybody gets to interact with everybody else, but only once. It doesn't get to interact, it gets to interact with somebody once every time step. So we have a clock, our computer has a clock, the clock divides the system into time steps, and in each time step we can choose randomly. It doesn't have to be randomly, you could have a procedure, it doesn't really have to be randomly, but randomly is a possibility. Let's see, this, who have I missed? This one, this one. Oh, that's it, that's enough, everybody's elected, and so forth and so on, each step.
I always get a bit confused at this point. So the Hamiltonian itself has interactions, like any one qubit can interact with multiple guys. why does he always interact just with a single other partner?
Now, that corresponds to saying the Hamiltonian is a sum of terms in which in each term a qubit interacts with one other qubit. And then when you exponentiate it, and do this trick that's called trauterization, it looks a lot like this. But I don't want to justify this now. This is not where I want to go. It's just that we're going to take this as a model. And we'll find this model is a pretty good model. All right. In comparing with black hole physics or ADS physics, and I'm going to restrict myself now. Well, actually, for the next equation, I don't need to restrict myself to the small black hole. We can have any black hole in ADS. How big should we take these time intervals? In other words, what is the natural time interval for comparing computer clocks with black holes? Okay, so I'm going to write the formula and talk about it just a bit. I'll tell you now, this time, the natural thing to identify this time with, or let's see how to say this. The natural time step, delta t, and by t here, I mean the time of the CFT here. The time of the CFT should be thought of as being beta, the temperature of the black hole, divided by 2 pi. If I have that right. It's the thermal time scale. It's the thermal time scale, and we'll talk around this a little bit. It corresponds to the, yeah, okay, we'll talk around it. But keep this in mind, that this is the identification that we should make about the computer clock relative to the clock in infinity, so to speak. Now, this is connected to something else. This is connected to the statement, and again, this is something unproved, but the statement that the complexity, or better yet, the number of gates in a circuit of this type, let's call it the complexity in some loose sense, the number of gates grows like S times T. But to think about that for a moment, for a typical circuit like this, randomly interacting, what is S? S is the number of qubits. Maybe there's a log 2, but I don't care about the log 2. No, what about, this is not right. This times time. S times T is the rate at which now, temperature times time. Suppose I have a black hole at different places near the black hole. Here's our black hole. Now we can go out to here, we can go out to here, we can go out to here. This could be an ADS black hole, it could be a Schwarzschild black hole, it doesn't matter. Clocks run at different rates. There are clocks at infinity, there are clocks near the horizon, they run at different rates. And so which T do I mean here? Well, it doesn't matter. How come? Because the scaling of the way time runs at different places is exactly inverse to the scaling of temperature. The product of temperature times delta T, anyways alone here, is the same. Temperature is an energy, time is time. The product of T times little t is a, what should we call it? It's an invariant with respect to choosing a location relative to the horizon. You can check that. Okay, so it doesn't matter where you stand. It also, the temperature times the time is also equal to something else. It's dimensionless. So it's a kind of dimensionless time. Doesn't matter where you go, how far from the black hole you look. And in fact, it's exactly the Rindler time, or it's with a numerical factor, it's the Rindler time. So if we have a black hole with a horizon, and we have different Rindler distances, the Rindler time is hyperbolic angle, and this product, temperature times time, independently of where you measure the temperature, is just this Rindler hyperbolic angle. Okay, so we can write this then in the form entropy, let's call it Rindler time, let's call it tau. Tau is Rindler time, hyperbolic angle. And what this formula says, if true, is the way that black holes evolve, the way they compute, is basically for each qubit, each one of these n degrees of freedom, it engages in one interaction, one gate, or in this case it's half a gate because we split the gates between pairs of qubits, but basically of order one gate per qubit, or per pair of qubits in this case, per Rindler time. That's the connection, if you like, between computer clocks and black hole evolution. The computer clock, meaning this clock here that divides us up in this way, is naturally connected with Rindler time. This is connected with another fact, which I've talked about previously when we talked about things falling toward the horizon, and it's just the fact that when people write the Lyapunov exponent e to the 2 pi over beta times t, they're actually writing e to the tau, tau being the Rindler time. Why do I think that 2 pi is, well, okay, we'll come to it. All right, now, we can generate unitary operators this way, just thinking of them as products of gates, dot, 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 Gn down to G1. We start at the right end, G1, G2, G3, G4. These gates here, or all of these gates here, sometimes it doesn't matter in what order we write them down here. For example, it doesn't matter the order of gates here and here. This gate commutes with this gate, commutes with this gate, because they act on different qubits. So within a block here, it doesn't matter which order you write them down. From one block to another, it typically does matter which order you write them down. But in any case, you just write down your product of gates. That's your unitary operator. And the thing we're interested in is what I'll call a precursor. Let's suppose that W is itself a gate, but in this case, let's say a 1 qubit gate. We're interested in U dagger W. This is what we can call this W of T. And that can also be represented by a circuit. Let's do the circuit. Somewheres in the middle of the circuit, we have a circuit for U on the right. We're splitting this thing into 2 parts. Splitting it into 2 parts. We have a U on the right, a U dagger on the left. The U dagger is simply the same set of gates except in opposite order conjugated. And so what the circuit for this thing looks like is we pick a gate and we act with the W. Sorry, we pick a qubit and we act with W. We can arbitrarily say this is the first qubit, we act with W, and then, I'm not sure if it's to the left or the right, but to the left we operate with the conjugate of this, and to the right we operate with the operator itself. The operator itself is a sort of mirror image of the operator on the left. And then over here, and so forth. And that's the circuit that defines the precursor operator, W of T. And we're interested, among other things, in the complexity of this circuit. Okay. Now you can see in the circuit here, I'm just reviewing now, you can see in the circuit here that there are gates that you can eliminate without changing the result. For example, this gate over here, which is some inverse, and this gate over here, you can pass this gate through over to here. I should have drawn it in mirror image. Now it's a mirror image. This gate cannot cancel this gate because W is in the way here. This is gate W, gate inverse, gate W, gate inverse. You can't cancel in general, the two gates here. But this gate and this gate you can cancel, and so you can remove. Meaning to say the circuit doesn't require these gates here. It doesn't require, let's see, these two I think we can also remove, and so forth. Some subset of them we can remove, and therefore in general the complexity of the precursor here is less than the sums of the complexities of the constituent operators here. It's always less than or equal. It can't be bigger, but it can be smaller, and in this case you can see why. Okay. Now, how do we calculate the minimum number of gates that it takes? How can we bound? How many can we erase in this way? We can erase all of the gates in this circuit. We can start on the right here and start asking when W acts. I used the word infect last time just to see what this means. This gate over here is going to have a causal effect on the qubit over here, and therefore affect this qubit over here. Now, in the next step, this qubit will affect this qubit. In the next step, this qubit over here will affect this one, and so forth, and there will be a growing, what I call epidemic of qubits, which will no longer commute with W. They won't commute with W because they've been acted on by gates which connect to W. And the same thing happens on the other side, exactly the same thing happens on the other side. And the answer is, the ones that you can remove are the ones that have been not affected or not infected by W. So we counted them last time. And we saw that what the answer was. I'll just review it very briefly. If we have we call the number of gates which are affected by W, we called it the size of W. It's a function of time, function of tau, namely how much tau we accumulate here. It's a function of tau. The size at tau equals 0 is just 1. The size cannot get bigger than the total number of qubits. So it starts as 0, it's bounded from above, and once you've affected everybody, they're all affected. So this is a function which basically monotonically increases and goes from, not from 0, but from 1 to n. All right. We used a computation, a little computation, a very elementary one, that showed that the change in the size when you go from tau, or from n, little n, to n plus 1, from tau to tau plus 1, discretely, was equal to n minus s times s. This is the average, this is statistical average, over n minus 1. And for all our purposes, this 1 is not important here. Where did this come from? Do you want me to review where it came from? No, I don't think I need to review where it came from. Or, thinking of this as a differential equation, we can solve it, and we find that the size after a time t, or a time tau, is n e to the tau over n plus e to the tau. This is the basic computation. Question? Yeah. Okay, in particular for, did I get, yeah, I got this right. For small tau, e to the tau here is small, n is big, we're assuming n is very big. This n cancels this big, this n, and the size just grows exponentially, simple exponential. So it starts out growing as a simple exponential. What happens at late time? At late time, this is much bigger than n, so the e to the tau's cancel, and the size asymptotically goes to n. Let's divide the size by n, just talk about the size per unit, per qubit. All right, that's very, very small to begin with. Well, it's exponentially growing. At some point, there's a crossover between the constant behavior and the exponentially growing behavior. That's at the scrambling time, and that's when n is equal to e to the tau, or tau is equal to log n. Call that the scrambling time. So it's some scrambling time which grows with n, and if n is very big, logarithm of n can be pretty appreciable. Let's put tau star over here. We have divided the size by n. That makes it very small to begin with. And in fact, it's a small function which stays very, very small until you get to within the vicinity of tau star, and then it basically jumps to about 1 rather quickly over a range which is about 1 unit of tau. Over a range of about 1 unit of tau, it jumps appreciably and then flattens out. In some approximation, we can just say the size is 0 until it's not 0, and then it's in. Now that, of course, is not exactly true, but it is a rather sudden thing. Okay, so that's what we know about size. As far as the number of gates, which I'll call the complexity, the number of gates after cancellation. After cancellation, the number of gates is the sum of all the gates that were there, uncanceled gates that were there up until time n, and the implication of that is that the complexity, the number of gates, is such that it's, well, okay, is equal to the integral de tau of the size of tau from 0 to tau. What is this saying? This is just saying that after a certain period, you just add up all the gates, but only the uncanceled ones. That means you add up all the infected people, and that's just this integral here. And from that, we can calculate the complexity. The complexity grows like a logarithm. The complexity grows like n log of 1 plus e to the tau over n. That's just integrating this formula here. And now if we use the fact that tau star, the scrambling time, is log of n, this becomes tau minus tau star. In other words, it's kind of a delay. There's a delay by amount tau star in the growth of operators. It takes them amount tau star to get started appreciably growing. And then once they start to grow, this takes over and begins to grow exponentially. Well, the logarithm of an exponential. So that means that this complexity starts to grow linearly with time. Okay, we can draw some. Yeah, okay, so here, this is what the,
So let me,
yeah.
so how long that window is of exponential growth is really just set by the temperature.
Well, it's the exponential during the, thermal time. If I were to plot the complexity over n, then it would start to linearly increase here. And the point is that the linear increase is delayed by amount tau star. So you get a free period, if you like, during which most of the gates cancel and the precursor doesn't start to become complex. And then all of a sudden it starts to become complex, starts to grow. This is a consequence of chaos, of course. Oh, here we are. Another point to point out is that, where was the size? Here's the size. It grows as e to the tau. This is the growth that is studied, for example, in out-of-time ordered correlation functions and so forth. And this e to the tau is e to the t over 2 pi t over beta with this identification. Now you can say I put this in by hand. I did. There was this comparison here which compels me to say that the time interval here has to be 2 pi over beta. Okay, what about size in Hamiltonian theories? The size in Hamiltonian theories is defined in a way, well, we can abstract out of this construction a formula for the size which goes something like this. Once a qubit has been touched or infected, it no longer commutes with the origin of the infection here, but it's more than that it fails to compute. In this theory of very discrete gates, it has a commutator which is of order 1. The effect of the system of gates, in other words, if you go from here, let's say up to the top, you have to go from here to here, then you go from here to here, and then someplace else you go from here to the top. The effect of being touched in each case does not diminish with the gap in between. It's like saying when you get sick, you get really sick, and it doesn't matter how far you are from the origin of the infection. That's something that needs to be shown, but it's true. In a random circuit like this, if you've been touched by the infected origin here, you will not commute with order 1 commutator. Yeah. Order 1 commutator. Okay, so here's a quantity that you can define the size in terms of. So take W, that's W over here, at time 0, and commute it with a qubit operator, any qubit operator on the ith qubit, as a function of time. This is the W at 0, this is the Heisenberg x sub I at a later time. This commutator will be very small. Well, okay, this is in the circuit model here, this commutator will be 0 until that qubit has been touched. Okay. Now square it, just to give you a number. Square it, take its trace, and sum it over I. Summing over I here, each one of these will be of order 1 as long as it's touched. If it's not touched, it'll be of order 0. Eventually, everybody will be touched. So eventually, this will be of order n. But this can be identified with the size. It's just this average or the sum of commutators. Everybody who doesn't commute contributes, and contributes something of order 1. That's one way of thinking about the size. But in this form, this can be applied also to Hamiltonian circuits. This is the basic form which goes into the out-of-time order correlation calculation. You're really interested, you're really not interested in the out-of-time order correlation, you're really interested in this commutator. But the commutator consists of some terms, WX, some of them are in time order, some are not in time order. And so you calculate. I'm not going to do that calculation. Okay, so Hamiltonian systems also have a notion of size. And from the out-of-time correlator story, together with some numerical studies and so forth, the behavior of this size here is very similar to this. It's not, I don't think it's rigorously equal to this function, but it has very, very much the same behavior. It exponentially increases, like the Lyapunov behavior, it saturates, and it also grows very quickly from a very small number to order n. Yeah.
I'm confused. So if I take a late time t where everything is infected, then this commutator, you said it's gonna be an order 1 for each qubit?
Yeah, so it'll be a lot of n, the size.
So why are you saying n is the size?
What?
Why are you saying n is the size?
Why do I
Size is
say
the
n?
number of gates, and n is the number of qubits.
And there's a number of qubits, every qubit gets infected.
But I thought you were saying here S is the size of the circuit, which is a bit.
No, this is not the size of the circuit,
Okay.
the size of the epidemic.
Okay, then, all right.
Size of the epidemic, not the size of the circuit. Okay. That's a good, in some sense, the size of the circuit is the complexity.
Yeah, exactly, right.
So you take the size of the epidemic and you integrate it,
Yeah,
and that gives you the size of the circuit, having eliminated the gates that can be canceled.
good.
Okay, so that's the basic intuitive idea of size, precursors. The switchback effect is just this fact that there's a delay in the onset of the development of either size or complexity.
So if we go back to the early model you described of having a bunch of sites where each site has a lot of degrees of freedom,
Yes.
how does the number of sort of local per site degrees of freedom enter this equation? Does it make,
N is a number of local degrees of freedom per site.
oh, right now this is all within one site.
This is within one site. This is within one site. This is the scrambling of information of a unit-sized black hole, or if you like, the scrambling of information before it starts to ballistically propagate.
Good. I guess the question would be, so how does that affect the overall spreading from one side to another? So the bigger
Well, that's
each
taking
site
place
is-
simultaneously, and it's there's orders of limits here. I mean, if the field theory is sufficiently big, much bigger the number of sites than in itself, then it will take a longer time than the scrambling time for it to ballistically propagate throughout the system. And so in that sense, the fast scrambling, this is the fast scrambling will take place fast by comparison, and then it will ballistically propagate out to a much larger system. But there are various limits that you can study.
Yeah, but the bigger each local site is, the slower the overall propagation
No.
from site to site?
No, it propagates, in the field theory, it propagates with the speed of light.
Oh,
In the field theory, it propagates with the speed of light. The speed of light is independent of the central charge, but to some extent, that's a normalization. Right. Okay, now, let's come to black holes, and what this has to do with black holes. We talked about the conjectured connection between volume. I won't talk about complexity, I won't talk about action right now. We can come back to that. That's itself very interesting. But let's just talk about volume. If we're interested in the complexity of the quantum state of this black hole, it's a Penrose diagram for a black hole. Incidentally, I'll work with a BTZ black hole for the most part, as I did last time. If you actually draw the BTZ black hole, this up here looks like this. But I'm not going to draw that. It gets in my way. Let's just draw it straight. I'm better at drawing straight lines and curves. Right, so I'll just draw the BTZ black hole like that. Okay, then there is this concept of maximal slices, maximal volume slices. It looks something like that. If you go right through the center there, t equals 0, the maximal slice is just a horizontal slice, and it has no extension behind the horizon. There is nothing behind the horizon at this point. So the volume, or the portion behind the horizon, what's called volume at t equals 0, is just 0. I'll identify that with the complexity of the initial state. Now what that leaves out is any complexity that went into the formation of the thermal field double state. And in particular, presumably there's an infinite complexity due to the ultraviolet behavior over here. But that's a sort of universal piece which is always there at any time and can be subtracted out. So now you go to a later time. A later time, it will look something like this. And it would still have this part that's outside the horizon, which is divergent over here, which would be the same as what's over here, but you now have some volume behind the horizon. It's that volume behind the horizon that we can think of as the growing complexity, but it is complexity relative to the complexity of the thermal field level, of the state at t equals 0. So when I speak about complexity, I'm speaking about the complexity in this sense here, the part that, okay, want a little more? You'll eventually, I tried to avoid drawing curves, but now I have to draw a curve. Well, I drew a curve over there. There's an asymptotic maximal surface that you tend to at late times. And not so late, incidentally. Fairly quickly, on the order of an ABS time or two, this gets pretty close to this asymptotic surface, and then it just proceeds to grow from the outer boundaries over here. Notice that this also goes into the past. And so whatever it is that's growing up here is shrinking down here. We'll come back to that. Question? No. Okay, so something's shrinking in the past, it hits a minimum and then bounces. It is not entropy. These black holes here have a constant entropy. It is not entropy. If the conjecture is right, then it's complexity. Okay, so the complexity grows linearly with time. In the past, in the white hole region, the point is the past here is a peculiar region. It's the white hole. White holes are unusual. We don't see them even through big telescopes. And we'll discuss why in a little bit. What is it about white holes which makes them unphysical, but we'll come to it. According to the complexity volume connection, it's a time during which complexity is decreasing. We've talked about this before. Entropy is a thing which we normally think of as increasing. It doesn't always increase. You can have situations where it decreases, but they're unlikely, and we'll talk about why in a little while. Okay. All right, now we want to add something. We want to add a precursor. We're going to apply a precursor on the left side here. Precursor built out of left side operators. That means U dagger, a simple operator W, U. And we're going to apply it right at time t equals 0. What does it do? Well, U dagger, I'm not sure which one is which. I always get my daggers and the undaggers confused. But one of them runs you backward to a time in the past. This is U of t. Let's write it out. U dagger of tau. W U of tau. One of them runs you backward. Then you apply W. W is a simple operator. What is W? First of all, what is W? I'm going to take W to be a simple operator which adds 1 bit to the entropy of a black hole. That's the least I can add to a black hole. What does that mean in terms of the energy carried by W? How much energy do you have to put in a black hole to increase its entropy by 1 bit? How much entropy does the black hole decrease by when it emits a Hawking photon?
What temperature?
Yeah, the temperature. Adding a bit, or adding a, so what I think of as W is not literally a local operator on the boundary. A truly local operator will, on the average, add an infinite energy. What we want to do is smear this operator over a thermal time scale. But that being said, W is a simple local operator, but it's been averaged over a thermal time scale. When you apply it, it creates a photon, or something like a photon. And that propagates inward. As it falls into the horizon, it blue shifts. Anything falling blue shifts. And in fact, the earlier you add it in, the more time it has to blue shift, and the larger the energy will be. Now, I have to be careful about what you mean by the energy. Energy is conserved on each side. So if I put in a little bit of energy on this side here, that energy is not going to increase. But what I mean by energy here is the energy that somebody, let's say, who falls in from time t equals 0 gets hit by. This is not the energy that you put in on this side here. This energy blue shifts in such a way that somebody falling in over here, or perhaps over here, it doesn't matter where, somebody falling in over here will get hit by an energy which depends on where this was put in. The further back in the past, the more the blue shift, or equivalently, the further back in the past, the tighter the distance between this wave here is and the horizon. Let's put it way in the past, it's very close to the horizon. And by the delta E, delta T, or delta X, delta P relationship here, if you hit something which has been squeezed, which is known to be within the horizon and some very small distance of it, you're hit. So the energy of what somebody falling through experiences is dependent on the time, let's call it tau W, the time at which the precursor was injected into the system, or which the photon was injected into the system. The longer in the past, the more blue shifted it gets. And in fact, how does the energy depend on TW? Anybody know? It grows exponentially, but only after TW is larger in magnitude than the scrambling time. Up to the scrambling time, not much happens. And then once you move past the scrambling time, this energy gets big. So if this time here is in the remote past, sufficiently, and then it grows exponentially. So after 2 or 3 scrambling times, the energy that this guy gets hit with can be more energy than the whole black hole. Wait 4 or 5 times, and it's much, much bigger than the energy of the black hole it experiences. I think it's fair to call this thing a pretty nasty firewall. So it certainly blocks passage into the black hole without what some people call drama. Okay, so we started without the firewall here. We calculated, well, we didn't calculate, I just said the complexity at t equals 0, by which I really mean the volume behind the horizon is just plain 0. Okay. What happens to the same maximal volume surface if I put this kind of shock wave in? Or equivalently, put in a precursor. The circuit now will contain this precursor, and we can expect that the complexity of the state will have added to it the complexity of the precursor itself. So we should expect then that whatever the complexity of the precursor is, that we should find it by calculating the maximum volume surface between these 2 points in the presence of the shock wave. Let me draw the picture and then give you a master formula, which is useful. I'll redraw this picture. Oh, the effect of this shock wave, it's a lot of energy, it could be a lot of energy. It does distort the Penrose diagram. There are 2 ways of thinking about the Penrose diagram. One of them is to actually redraw the Penrose diagram to account for the shock wave and the energy of the shock wave. The other is the trick of Dre and the Tuft. Does everybody know the trick of Dre and the Tuft? Okay.
So does that hold even when the energies are comparable or even bigger than those?
Is what hold?
Like that's not a perturbative statement, this trick? You can sort of,
No, it's very definitely not perturbative. The Tuft Dre,
Yeah.
no.
that works for very high energies.
Yeah, works best to higher the energy. Absolutely. Okay, the Dre and Tuft picture. On a true Penrose diagram, light rays are always just light rays at 45 degrees. What Dre and Tuft pointed out is that you can use a slightly different representation of the effect of the shock wave. Here's a shock wave, and in the other representation, you don't redraw the Penrose diagram. What you do is you account for the shock wave by saying that all trajectories that go through the shock wave get pushed and come out up here. The amount by which they get pushed up here is dependent on the energy of the shock wave, and I'm not going to work it out in detail. This, of course, is in the papers by Douglas and Steve, and other people, and Dre and Tuft in particular. The effect of a shock wave is to displace any trajectory coming through it and to push it upward along the direction of the shock wave by an amount which depends on the energy of the shock wave. I'm going to use that picture to draw a picture of what happens, but then I'll give you a detailed formula which pretty well captures the effect of the shock wave on the volumes of slices. It's a useful formula, and we'll see how it relates to things we've discussed already. So we don't redraw the Penrose diagram. We draw in the shock wave, which I'll imagine is in a fairly remote past, so it's close to the horizon. All right. Now we want to draw a maximal surface connecting these 2 points. Keeping in mind, when that maximal surface crosses the shock wave, it gets pushed back. It goes way back. What does it look like? And now I'm not doing the calculation for you. I'll just give you the picture. It looks approximately like this. This goes up here. Then this jumps back. If the shock wave is very energetic, in other words, if this was put in long in the past, it jumps back a long way and goes like this. That's about what it looks like. But now notice that there is volume behind the horizon. There's volume behind the horizon here, and there's volume behind the horizon here. And this volume behind the horizon over here was not there without the shock wave. So, putting in this precursor has done something to increase the portion or the volume of the surface behind the horizon. And now let me write down the master formula. The master formula is, given a shock wave coming in at time tw, in other words, given a perturbation at time tw, and let's generalize this, picking a point t left and another point t right, tau or t doesn't matter very much, and constructing the maximal surface as a function of 3 variables. As a function of 3 variables, and I'll write it out for you. This is not exact, but it's the formula that actually is due to Douglas, and it captures all of the features except some of the very fine detail at small times. It's good for large times, but it's good for times, I would say, comparable to a thermal time and bigger. Okay. The formula is the volume is proportional to, there's a factor of proportionality. Somebody can figure out what that factor of proportionality is, but I'm not interested in that. That's proportionality. That volume is equal to the logarithm of cosh tau left plus tau right over 2. One term. Basically, I think that term has to do with the first piece up here, and then there's a second term which has to do with the piece down below. It looks like a plus E to the tau W, the magnitude of it, minus tau star, the scrambling time, then plus tau left minus tau right over 2. If you want to go through the exercise that's that Douglas did, you have to read the papers that he and Steve wrote. This is the formula that comes out. Or this is the approximate formula that comes out, then we gotta close up this bracket over here. Okay? If you're interested in this kind of thing, this is a useful formula which generally does capture how the volume grows. This volume here has a prefactor in front of it, which has G, what does it have? LABS's, I'm not sure what this form here. Okay. Let's ask now, let's go back to what we were talking about before, where we start at the thermal field level. Oh, this term here is there because of the shock wave. Without the shock wave, this term would be here. Without the shock wave, and tau left equals tau right, cosh will equal 1 and log of 1 is 0. So that's picking up just the zeroness of what's going on here. Now let's throw in a precursor. We'll flip the precursor, you go down, you go back up, and halfway through, you throw something in.
Is there a sign error there?
What's that?
When you add tau left and tau right?
I think there's a verbal sign error, but I think that's.
Sorry? What are you asking? Is there a sign in it? No, I don't think.
So the tau left is equal to tau right.
I think time is up on in the opposite direction of the left.
Time is up on both directions.
Yeah,
So time-
what he
time
meant to
is
say,
up on
tau
both
left is
directions.
minus tau right. The equation's right. I think he
Equation's
was,
right,
yeah.
Time is up on both directions. Right.
I think it's just, yeah.
Yeah. You'll see, it's nice, it works well. Let's now throw in something at dW here. Okay. And recalculate what we get, again at tau left and tau right equals 0. That should be just the complexity of the precursor. All right, so what does that give us? That gives us logarithm of 1 plus tau left is equal to right, e to the tw minus t star. Tau w minus tau. Now what is tw? Tw is just the time in the argument of the precursor. This is exactly the formula that we got by integrating the logistic function. So this agrees in that sense with the calculations coming from the analysis, the naive analysis of the circuit. And in fact, it's probably a little bit too good in the sense that why should it be exactly? Well, I suspect it's not exactly. This formula is not exact. But it captures some very similar physics. Okay. Good, everybody? This can be, as a huge generalization of this, and where you put in all sorts of out and in time order operators. So this can go up and down and up and down and up and down, and each switchback here, you can put an operation in. You can also put operations in that are in time order, and you can check, you can do the circuit analysis, you can do the general relativity analysis, and they agree. They agree to the same extent that disagrees. So it's pretty clear that the counting of gates in a quantum circuit is closely related to the evolution of volume in the black hole. All right, now let's talk about this idea of a second law of complexity. The complexity always tends to increase. Well, it does unless it doesn't, of course. It's like entropy. Entropy increases unless it decreases. How can you make something whose entropy decreases? You just take something whose entropy increases and you run it backward in time. If you could change the sign of a Hamiltonian, you could run it backward and you would find the complexity decreases and so forth and so on. Why is it then that complexity always tends to increase? Not complexity. Complexity or entropy, everything I'm saying would be the same for both of them. In what sense is it? Well, it's in the following sense, that let's say decreasing entropy. You run backward an explosion. If you ran it backward, Humpty Dumpty would reassemble himself. It's unstable. Unlike what happens when you go forward, where entropy increases, if entropy is increasing, if you perturb it a little bit, the increase of entropy will just continue along with very little change due to the perturbation. If entropy is going backward because somebody's gotten into the system and done something crazy, and then you perturb it just a little bit, after a relatively small amount of time, the whole system will know that something was perturbed and it'll turn itself around. I would say the same is true of complexity, exactly the same is true of complexity. And later on, we'll talk about the analogy between entropy and complexity. But for now, let's just take it as a given that complexity tends to increase in the same sense that entropy tends to increase. If you take a quantum circuit, and that quantum circuit, and when I say complexity, I mean quantum complexity. If you have a circuit and you run it forward in time from some state of small complexity, well, it's got no place to go except for its complexity to increase, but you can also run it backward. If you run it backward, its complexity will also increase. It's got no other place to go. Okay. So again, given a circuit where complexity increases, you can construct a circuit by just changing the sign of the Hamiltonian, for example. You can construct a circuit whose complexity will decrease. But the expectation would be, and can we prove this? I think we can prove this, but it's, let's take it as a hypothesis for the moment. The reason that complexity tends to increase is because decreasing complexity is unstable. If you hit the system a little bit while its complexity is getting smaller and smaller, then after, how much time will it take before the global complexity will start to increase? Think about that for a minute. You have the circuit, and it's running backward in time. If you hit it with the unit operator, nothing happens. It will just continue to go, complexity decreasing until it gets to the minimum. What happens if you hit it with a W, with a genuine precursor?
Just scrambling time.
Scrambling time. By a scrambling time, the whole system will know it's going in the wrong direction. So what the expectation would be that if a circuit is running backward in time and you hit 1 qubit, then after a scrambling time, it will surely be going Oh, well, surely is a loaded word. Surely means pretty sure. No, exponentially.
More
sure. Morally sure. Much more than morally. Much more than morally. Incidentally, the sense in which complexity tends to increase is much stronger than the sense in which entropy tends to increase. It's exponentially stronger, but we'll come to that. It's a much stronger thing. So let's see if we can confirm that complexity decreasing. On this diagram, before we put the shock wave in, the complexity was decreasing. How did it get that way? It got that way because somebody in the very remote past did some remarkably clever thing and created some extraordinarily complex state with a complexity running backward. Okay, I don't know who that was. It doesn't matter who it was. They did it. It could be the result of a quantum recurrence. It could be the result of a quantum recurrence where after a sufficiently long time, every quantum system will just recur. But it could also be somebody very clever, some army of Maxwell demons started the system going backward. And it'll go backward until it reaches some minimal complexity, in this case complexity 0, and then it'll bounce and increase again. Okay. Is this decrease of complexity stable? So let's go back in time a ways to TW and hit it with one thermal photon. And let's examine the evolution of the complexity as a function of T left. I'm going to hold T right fixed. I'm focused on the left side here. I'm going to hold T right fixed, and I'm going to study what happens to the complexity as a function of time, having flipped it with TW. Okay. Let's just do it. Okay, so let's see what we need here. T right is being held at 0. It doesn't matter whether it's 0. It could be held at any place, but just for simplicity, hold it at T0. Log cosh tau left over 2 plus E to the tau W minus tau star plus tau left over 2. Okay, so let's see now. Tau left is negative now. I'm interested in the remote past. Tau left is negative, so what is this thing doing as a function of tau left? It's decreasing. Tau left is negative. Yeah, here's a picture of Kosh. Kosh decreases when the argument is negative. So this is decreasing as a function of tau left. Everybody agree with that? Good. This one is increasing as a function of tau left. There'll be a crossover. The crossover will be when tau left over 2 is equal to the thing in the exponent. Incidentally, for large, there'll be a crossover. They're going the opposite direction. When tau left is very large, tau left is very large.
Okay, right. It might come up.
Yeah. When tau left is very large, what do we say when tau left is very large? No, tau left being large in the future.
That's good, right?
Hmm?
Yeah, so then you have a growing complexity, and you get the inverse, so it's good.
So let's see where they cross over. Very far in the past, it will be decreasing, and then at some point it will cross over, and it will cross over when the thing in the exponent here is equal to this. So what is that? That's tau left over 2 equals
Large and negative.
large and negative. So the tau left is equal,
Be the mass tau range.
Star minus 2.
is equal to tau W, no, is equal to tau star minus tau W.
Oh, yes, nice.
Okay. What this says, if I get it right, what this says is by the time a scrambling time has evolved, tau star, the crossover has happened, and the decrease of complexity has, or decrease of volume in this case, has morphed into an increase. So you see, in that sense, that the decreasing complexity, that changed sign of course at t equals 0, is unstable if you go far back in the past, put a small flick in. How far back? Bigger than the scrambling time. Go far back, give it a little perturbation. After a scrambling time, it will turn around. Ultimately, I think this is the reason that there are second laws in the first place. Second laws in the first place, both kinds of second laws. That it's not that the opposite can't happen, it's just that the opposite is unstable. And we see it here directly just from black hole physics. Just from black hole Einstein physics, together with a little bit of patching across shockwave geometries here, we see the instability of the decreasing volume here, and interpreted as complexity. Well, it is what it is. Okay, that's it for today. Next week, what are we doing?
Jordan, where'd he go?
Okay, I think Jordan was gonna talk about.
Who?
Jordan?
Jordan.
I think he